Hello again, folks. Today we're going to be covering section 7.1. Okay, just to look at the calendar here. This video is for Tuesday, June 14th. So per the schedule 7.1, right on schedule. The packet that I have for you consists of these pages. This is a resource. I'm going to use this as something of an axiom. Sort of, it is what it is kind of definition, specifically for the rays. All right, this is a nice diagram. I took it from another textbook. All right, and then I included this as a schematic, pardon me, a scaffold, skeleton, whatever you want to call it. I want to point out a certain terminology and some abbreviations that you might see as a symbol that doesn't get mentioned elsewhere in the subsequent diagrams. Now, here's another thing that I swiped from another resource that I just love. This is copies of different alphabets. What is of importance to us is the Greek alphabet. And I want to highlight certain letters that would be useful to know in the subject. And then there are some diagrams that I kind of hodgepodge together. I'll go through this with you. This is about measurements. Whether you're in degrees or radians is what's relevant to us. There is another type, gradians. These are angles that are good to know. In the long run, you may want to remember these, or at least have a reference handy. This is a model that I came up with for converting between units. All right. This is the basic idea. This is if you have several conversion factors that you need to incorporate. A lot of problems are like that, especially in a science class. This is more or less a comparison between what are reference angles and coterminal angles, right? This is, although it's mentioned in section 7.1, is really going to be more important further down the pike. But there are some formulas that would be good to have on hand. This is what we're going to be dealing with primarily, right? Coterminal angles and what to do. To find something that is in the same location but using smaller degree figures. All right. Then there are some formulas that were taken, these are nice from the textbook, for the area of a sector and the arc length, and then some formulas for linear and angular speed. All right, I'm going to give you an example for each of these. I'll just write them next to them. And then a diagram I made deriving these formulas and some others, right, as a result of that. Okay, and then some word problems. Okay, so if you're following along, maybe have a highlighter handy, and I'll try to point out what's relevant from here. Put that aside, and turn on the projector and adjust the lights. Okay. See if I can get this out of the way here. There we go. Pick up. So blue. Okay. This is a packet that has many, if not most, of the diagrams that are relevant. I think I'm going to leave the actual thumbnails right now because they might be useful today. Actually, you know what? All that talk, and I didn't even tell you about my little picture here. So, if you were to read this in our textbook, it's kind of all over the place. The actual section 7.1 is about angles. It's more or less an introduction to that. All right, but there's naturally vocabulary, all right, which I want to cover first. All right. And then there are actual measurements and conversions. We'll do that second. And then the last thing would be basically the physics of this, which would be arc length, area of a sector, angular, and linear speed. All right. It's good to memorize certain information. This is probably the most practical thing. Converting between radians, a type of unit of measurement, and degrees, vice versa. And the subtleties of that. There are there's a third thing. If you want to convert to actual Pi Radians, you just don't multiply by 3.14 or divide by 3.14. You just leave the pi symbol, right? Okay, so think about, we're going to do this basically. We're going to go through vocabulary and symbols first, do some conversions, talk about measurements and conversions, and then have some examples that are basically physics. Okay, back to the slides here. And I'll get this out of the way now. Alright, this diagram I like. It's from a different textbook entirely. Because it illustrates, hopefully these are good choices, we'll find out the hard way. What array looks like, and I'm kind of using array in an axiomatic way, being that it's like the foundational is what it is thing, right? There really is earlier definitions. But what's relevant to us is angles, so this is the more basic concept, all right? Array can be named by 2 points on the ray, all right? And the order is very important. So the endpoint, all right, is usually, well, I should say it has to be the first initial in the sort of abbreviation. So if you see array that is in this order, A endpoint, and then B is just some other point on the ray, the abbreviation for that would be AB with a little arrow drawn above it. Right? If on the other hand you're starting with the letter B, all right, even if it's oriented A, B, left or right, just as it is above, all right, B indicates in the abbreviation that that is the end point. All right, so it's important. All right, the only thing from this that I really want you to take away from it is what array is, what array would look like, and basically the abbreviation. So know this stuff. Okay, anything else is just gravy. Okay. Now, if you're in the packet, if you have printed it, let's go through some terminology based upon that. All right. There's several terms, and I may have to shrink this. Okay. Maybe even enlarge it. We'll see how well we can get through this. This is a crummy blue marker. Okay. So I'm going to put this marker aside and hope for the rest. Okay. Right. There's 6 terms, yep, that I want you to know. So I'm going to put little bullets here. All right. They're not mentioned explicitly in the other diagrams that you see, so it's really important to kind of have them at the ready, have them clear. All right. Turn this around. Sorry. Working in the dark is always a trick. I'm going to leave it like that so I can see a little bit. All right. First word that you most know is the word angle. All right. And an angle is based upon the idea of array, which is the reason why I mentioned it. All right, what is an angle? All right, it is the union of 2 rays, all right, at a common endpoint. All right, the common endpoint is a vertex. It's referred to. All right, it's a corner, more or less. Now, to give you some idea, there are some pictures. I'm going to draw a very simple picture here, all right? And then there's the actual sort of abbreviation that you might write. Here's a simple one, all right? Array pointed in this direction. I'm going to put 2 dots here. And then a second ray united to that, heading off in another direction. And they're joined at the vertex point here. If they happen to have letters attached to them, all right, they might just be something like this, all right, A, B, and C, all right. In which case, if you are going to abbreviate, that is without drawing the picture, the symbol you would see is pretty much that in alphabetical order. The vertex is the initial that really should be in the middle. So if you're going to use all 3 letters, it's going to be A, B, C, right? If you refer to it, let's just say backwards, reading from C through B up to A, then that's fine, all right? But just make sure that the B is the middle initial if you're going to use 3, because that is again implying something. It's implying that that is in fact the common endpoint. That's the vertex. All right? There are more concise ways of referring to an angle. All right, you might just refer to the vertex. All right, some people just say, well, this is angle B, or they might use a Greek letter. A lot of times they would put it on the inside here, say something like that. Or they might just use a number. Right? That's why I've included basically this table, which I wanted to show you now. All right? If you have this printed, and it's going to be a little bit of trouble because unfortunately it's superimposed upon my scribble here. This book is using maybe like 5 different Greek letters from the list in the Greek alphabet. All right? My personal favorite, and maybe I'm corrupted because I was a physics major, all right, is theta, all right, which is, if this is alphabetical, further down the list here. All right. There's really 2 that are, they'll use one and then another if there's a second angle. Where is it? Theta. Oh, here it is. All right, sort of highlight this. All right, on this document if you're following. Theta looks basically like that. It's used, again, as a Greek letter in lieu of a Roman letter, like B, all right? Or this phi further down the list, all right? Which is sometimes, there's a fancy stylized version of it like that, or just this sort of no smoking kind of cross-out symbol, all right? They have a tendency in physics books to use theta and phi, all right? This book does do that, but it also uses lowercase alpha and beta and gamma, all right? So when they're talking about an angle, all right, sometimes in here they'll just say, they'll put an arc and then they'll put the alpha symbol, all right, if they don't put it on the corner itself, all right, or beta, all right, or gamma, okay, which is more or less ABG, all right, as a transliteration, right? I love this because I actually got this from a dictionary that I don't even have the dictionary anymore. This was on the inside cover of the dictionary, and whoever crafted this was, deserves some serious respect. Why? Because they decided to illustrate via comparison, right, Indo-European alphabets, right? It's not Hindi, unfortunately, but it does include Arabic at least, all right? And you see the similarity by sound, all right, and shape of the letter. All right, so I thought that was kind of cool. Anyhow, for our purposes, math, all right, no alpha, beta, gamma, theta, and phi, all right, by sight. All right, now back to this. Mess out of the way. All right, the measure of an angle is the amount of rotation between rays. I'm going to use a different color just to make this a little bit easier to read, and maybe close that curtain just a little bit. It is the amount of rotation between rays. There's 2 words that I'm avoiding right now because I have a diagram to use those 2 words. All right, terminal and initial side, but this is enough just based upon what we know as a ray. Right? It can be measured in degrees. It can also be measured in something called Pi Radians, or the decimal equivalent, which is just regular ordinary radians, or even another option, which would be gradients. All right, more likely you'll see it in degrees, at least initially. All right, the abbreviation written in a formula is a lot of times an italicized M and then this symbol, and then whatever symbol you're using to refer to the specific angle. So I'm going to put a question mark. All right. Then there's this concept, the sector. All right, in relation. Well, you know what? Let me do myself a little favor and switch two things around. I'm going to talk about a unit circle first, and then a sector. Okay. Essentially, a unit circle is a circle, all right, centered at the origin, so at 0, 0. What that is implying is that you have a circle. There's more to it in a moment. It's a circle centered at the origin with a radius equal to 1. Okay. But what is implied by that, and 1 watt you might wonder, whatever the unit is, right? 1 unit, right? What is implied is that if you have a coordinate plane and you have a circle sort of superimposed upon it, so I'm going to just scribble that, the center of the circle would be right at the origin, all right? And the radius that would extend from the origin to the edge of the circle would be a radius of equal to 1 unit, whatever it is, right? That is a unit circle, right? A sector would be an area basically between rays and when the vertex is at the origin as well. And the rays intersect. There's a lot to fit in here, unfortunately. An area between the rays when the vertex is centered at the origin, so 0, 0, and the rays intersect the edge of the circle. All right, that's why I mentioned unit circle first. All right, so essentially, if you had, just to sort of illustrate, if you had a circle centered at the origin, and then you had a particular angle, like so, the area that would be in between, all right, the rays that form the angle and the edge of the circle where it's intersecting, all right, is known as a sector. There's a less complicated way of saying that, which I like, which is to simply call it a pi wedge, right? If you've ever eaten pie, all right, I'm sure that you know, all right, what a pi wedge is, right? It's something like that. It's just that sometimes the pieces are very generous, right? So it doesn't have to be a skinny little pumpkin pie wedge. It could be the whole thing. The whole kit and caboodle, the whole circle would technically be, you know, a sector if you want the whole area. But then they would call it the area of the circle instead. Okay. All right, now because I'm a little short on space, I'm going to erase a little bit, but you can put whatever you were going to. The additional 2 terms, all right, that I wanted to include were these. The arc length and what is known as quadrantal angles. All right, so I'm just going to put this here for reference, and then I'm going to fill in the void. Arc length, and then quadrantal angles. Those are the remaining terms. All right, that would be good to know because they're not really mentioned too explicitly elsewhere. Okay. I'm hoping that there was 1, 2, 3, 4, 5, 6 spaces that was enough to write. My projection is a little bit hard, and my markers are quite thick. So I'm going to erase a little bit and then give you definitions for these, just more or less up here, to organize. might be wondering, why are you making us write this, buddy? The reason is because if you physically write something, you're more inclined to remember it. Right? That's really only my logic. All right. Anyhow, an arc length is denoted by the letter S, somewhat weirdly, right? You'll see a formula for that later. Radius times theta, so radius times an angle, right? But it is basically the length of the curve formed by basically the edge of the circle, right? Formed by rays, two rays, and there's a funny phrase which I feel compelled to tell you. Let me change one word here. The length of the curve, it is essentially the edge of a circle. That's the easiest way to refer to it, but just a segment of it. A segment of the edge of a circle, all right? Just a portion of it, not usually the whole way around. That would be a circumference. All right. Between two rays, and I hate to use this word, but I have to, subtended, right, which basically means formed by, right, or as a result of an extension of something, from what is known as a central angle. That's a mouthful, right? But that is technically correct, right? Just to reiterate, all right? The length of the curve, all right, between two rays and subtended from a central angle, right, is known as an arc length, right? What is it in a practical way of thinking about it? Just as a sector is basically a pi wedge, an arc length is a segment of the edge of the circle, all right? So if it is more clear that way, that's fine, all right? I would just be remiss as a person who teaches math not to give you some kind of a formal definition as close to formality as possible, okay? So one more, and then we're moving on to actual nice diagrams, all right? Quadrantal angles. All right. There's, I guess, technically 5, but one of them, or 2 of them are the same place. They're coterminal. It's noteworthy angles measured to an axis, right? Noteworthy angles measured to an axis. Not that boring, am I? This one is on its way out too. So, and what I was hoping, and again, I would hope that you have more space, my projection is not really cooperative. If you think of basically 4 coordinate planes, like this, and I'm going to highlight this in red, all right? An angle that would be good, that would be measured on an axis, would be, in theory, 0 degrees, if you're reading in degrees, and coincidentally also 360, because that would be the whole way around. They're what you would refer to as coterminal. This is a forthcoming concept, right? They're the same location, right? If you measured an angle up to the y-axis like this, this would be 90 degrees. If you measured it to this point, this would be 180 degrees. If you measured it 3/4 of the way around down the y-axis, this is 270. And if you went the whole way again, you'd be at 360. So know that 0 degrees and 360 are coterminal. They're in the same location, essentially. All right. It would be a situation like that. All right. 90 is the L shape, all right, from the axis of x 90 degrees. A straight line is 180, all right. 3/4 of the way around is 270. It would be good to commit these at least to memory, all right. Noteworthy angles measured to an axis, all right, or quadrantal angles, all right. All right. Anything else is mentioned in diagrams, so let me shift gears now. And I'm going to get rid of the thumbnails because I think it's making the projections too small. All right. All right. Go away. All right. Now, there are some things I alluded to. All right. Just a moment ago. This is another diagram that I swiped from a different resource, namely a different textbook. You'll hear this phrase thrown around, standard position. What is standard position? Standard position is when the vertex is at the origin, so 0, 0, if it's superimposed upon a coordinate plane. And what is referred to as the initial side is running on the x-axis. So just to illustrate, if you had this superimposed upon the x-axis like so, and that's the origin, all right? The initial side would be here right on the x-axis, all right? And you read the angle counterclockwise, which means that you're reading this way. All right? That's considered the standard, all right? Of standard position, right? This other side, the side that you actually read, all right, is illustrated here as well. This is known as the terminal side, right? This is the side you read the angle from, all right? All right. Now, how do you actually do that? Well, you have a device known as a protractor. I'm sure you've probably seen in your life, all right? Here's a protractor, all right, rigged up in the normal way. This is measured from what would be 0 here. Again, if you can imagine this on a coordinate plane, here's 0, here's 90 quadrantal angles. The terminal side would be here, all right, and this is read as 50 degrees. All right, you read the inside. And unfortunately, if you want greater precision, you have to read the edge, but not confuse it with the coterminal. Well, it's not technically coterminal. This 130 is over here. It's the thing upside down is what it is. You read the smaller numbers, 10, 20, 30, 40, this way, counterclockwise. That would be a positive angle, right? You can read something backwards, but if you do, it would be regarded as a negative angle. So make that distinction. Okay. Here are some angles that you may know, but are also still good. This is again swiped from another resource. Right angles are the L shape. They're exact when the angle is exactly 90 degrees. Acute angles will be something between 0 and 90. Obtuse angles would be something between 90 and 180. And a straight angle would be 180. I want to say there's another one, a reflex angle, but it's not really immediately important. All right, a reflex angle would be between 180 and 360, I think. Okay. Now, the angles that would be good in the long run to commit to memory, you see here. All right. These are the angles that are as they are written in degrees, which up to this point, I've taken for granted that you're familiar with degrees, right? You've probably heard, if you've ever had high school geometry, I would bet you probably know about degrees. Anyhow, a handy way, literally handy, right, to remember 30, 45, and 60, and 90 is with your actual hand, all right? If you can imagine, my hand doesn't stretch very well, but you can imagine the sort of L shape as being 90, then halfway would be 45, right? And between 45 and 90 is 60, all right, in this orientation, and between 45 and 0 would be 30, right? There are equivalents of them though, and this is why I mention it, right? Which you see here as basically fractions of pi, all right? These are in degrees, but the same things can be referred to in Pi Radians, all right? What you would think of as being basically fractions of pi. Okay? There is another thing you can do actually, which is to go a little bit further and actually convert it to a decimal. If you were to replace the pi symbol with the decimal equivalent, 3.14159, however many degree, what do you call it? How many decimal places you'd like for greater precision. If you actually multiplied by the number 3.14, you'd get the decimal equivalent, right, of radians, right? If you see the actual pi symbol, it's referred to as pi radians. What's the benefit of having this? It preserves all of the infinity of pi even without acknowledging it, because you can't, right? But this is, when you have actual pi radians, it's a little bit more satisfying because, and especially part of a calculation like angular speed later on, you would need a decimal, right? It's a little bit more warm and fuzzy because we're used to everything being in decimals versus fractions. But the fraction is actually exact, whereas a decimal is somehow rounded. Anyhow, what you may notice, and we're going to go through the process of conversion, 0 is in the same place as 360. 360 is 2 pi. That would be the whole way around. All right, 90 is a fraction of pi. It's half of pi, literally. All right, would be good to know at least these 30, 45, 60, and 90. All right, and what their pi radian equivalents would be. 30 is pi over 6, 45 is pi over 4, 60 is pi over 3, and 90 is pi over 2. All right, so try to strategize that you commit some of this to memory, right, in the long run. If not, you could always brute force figure it out, but like sometimes a bit of a chore. All right, let me give you this last reference, and then we'll get to some problems. All right, there are these two concepts. There's probably an overlap somewhere, but this is the segment of the textbook I swiped this from. All right, I just don't like the order in which it's written. So I'm going to talk about reference angles first and then coterminal angles instead. All right, I alluded to this just a little bit a while ago. Look at this diagram here. We're interested in a reference angle basically in the future, like maybe section 7.2 and thereafter. All right. These will be useful when we get into the subject of special right triangles, which you may have an inkling about if you've ever heard of the 30, 60, 90 degree right triangle and the 45, 45, 90 degree right triangle, all right? If you have some angle, right, that can be converted essentially to these reference angles, that helps when you're basically answering a problem. So there isn't anything that you have to do with this immediately, but it does get mentioned in section 7.1, so kind of save it in the back of your head. Reference angles are what we want to sometimes convert funky, angles that are given to us randomly into, right? Why? Because we could relate them back to something called special right triangles. It hasn't really been formally discussed yet, all right? Here's the actual definition, all right, here, and I'm going to highlight, all right? An angle's reference angle is the size of the smallest acute angle, right? And it's abbreviated by T prime, all right? Formed by the terminal side, that's the side you read, all right, of the angle, and, all right, the horizontal axis. So if you had an angle that was in, say, quadrant 1 like this, all right, then this is sufficient. This is an acute angle. All right, you're just going to stick with it. The reference angle is the same as the actual angle, okay? When you have an angle that is instead measured over to quadrant 2, all right, Roman numeral 2, all right, you want to refer to the same place, all right? This angle here that would stretch here would be something like 135 degrees, all right? But for the sake of incorporating special right triangles, you would read it backwards, all right? You would read it from still the x-axis, but you would read it in this direction, all right? Why? Because you want to attempt to draw a right triangle, essentially. There's a formula here. If you wanted to determine, all right, the reference angle, T prime, you would subtract from 180. How come 180? Because you're over here in terms of you're in the second quadrant is the bottom line. So you could say pi minus the angle that you're reading, all right, as long as it's in pi radians. Or you could use the degree equivalent, 180 minus T, right? If you're in the third quadrant, all right, you're going to have an angle, in theory, if you've gone this far, right, that's beyond 180, right? So in that event, the reference angle prime is going to be subtracting by 180 instead of subtracting from 180, right? Or you could use you could use the pi symbol instead, as long as you feel comfortable with a fractional equivalent of something rather than a degree equivalent, right? If you're in the fourth quadrant, again, in this instance, you're on the other side. If you've wrapped all the way down to here, all right, in the fourth quadrant, you would want to refer to this part of the x-axis, and you would read from this direction, all right? So the reference angle would be subtracting from 360 instead, in this place, all right? All right? This is, again, it's not immediately important, but it's forthcoming when we get into that subject, special right triangles, the 30, 60, 90s and the 45, 45, 90s, all right? What is more important is this, the other half of this, the coterminal angles. Let me get the gobbledygook out of the way. All right, and this is a bit of a procedure. When is this relevant? These will be useful if you're basically trying to translate these would be useful to translate to while dealing with awkward negative angles, right? You're given a negative angle, or if you have an angle that is greater than 360, so it would be a lot of turns past 360 per se. Why? Because the logic is it's essentially easier to work with smaller numbers that represent the same place. That's it, essentially, right? So, if you're given essentially a negative angle, as an angle would be if it's less than 0, you're going to add 360, or in theory, if you have pi radians, add 2 pi. However many times as you need to get into the normal spectrum, right? The normal range. I hate to use the word range, but when you want an angle that's basically between these figures. Between 0 degrees, you want your angle, whatever, I'm going to use theta, all right, to be in the range, normal range of 0 to 360. All right, that's how many times it will take you to add 360 if you're given a negative, right? Maybe once, twice, depends on the number. All right. If, on the other hand, you have an angle that is greater than 360, all right, you're going to subtract by 360. Or if you're given a fraction of pi radians, subtract 2 pi. All right. Here are the examples that I'll go through with you in a moment. Negative 45 and 800 degrees. All right. I'm going to come back to that because I absent-mindedly skipped a couple of things in my notes here. All right. So let me review this diagram basically. All right, the different units that we have to choose from. And then we'll do some conversions, and I'm going to come back and talk about these things again. Okay. If you take a look at this, these are basically our choices for different types of units to measure angles. All right. The ones that are really relevant to us are degrees and radians. There is this other concept of gradients, so I figured they're worthy of mentioning. All right. Basically, think about it this way. All right. A circle, all right, superimposed upon a coordinate plane, so x and y plane. The maximum in one turn would be 360 degrees all the way around, right? But that's kind of arbitrary, right? Who decided that it should be 360 degrees? The truth of the matter is the Sumerians decided, right? So, and then we acquired this information via Babylonians later in history. So basically, a culture from at least 5,000 years ago, all right, who had a number system that was based upon 60, all right, is the reason why we have a circle chopped up into 360 increments. All right, why? It's not a coincidence, probably, that the number 360 and a calendar is 365. It would imply that they had something of an imprecise calendar. That's my best guess. All right, their counting system of 60 works well with this number. That is maybe a better explanation. But why the number 60? Because they did count on their fingers, all right, in their hands, but they may not have done it the way that we do. We have a whole finger to represent a number, right? 1, 2, 3, 4, 5, and then another hand is 10 total, right? That's intuitive to us, a decimal system. It is believed that they used to count the segments of your finger, which there are 3 basically under normal conditions. So you would, with your thumb, count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 1 is 12. 12 times 2 is 24, 36, 48, 60. So 60 was intuitive to them in a different way than it is to us. All right? And they made that they broke up their calendar, I would guess, into 360 days because it jives with the system of 60. All right? It's kind of peculiar. Anyhow, it works, it's just kind of arbitrary. An alternative is radians, all right? And this is instead based upon, it's still chopping up a circle, all right, on a coordinate plane, but doing it based upon arc length and radius, all right? So the situation basically, when the arc length is the whole way around, that's a circumference, right? Right. Which would be what? A circumference is pi times d, or 2 pi r. Alright, if you're going to break up a diameter into r's instead, there'd be 2 of them. And then a radius on the bottom, alright? That means that the maximum, if you went the whole way around rather than just a segment of it, would be 2 pi instead, alright? And then there would be fractions of that, right? Basically, a radian is, this 1 radian is the situation when the arc length is exactly equal to the radius. In other words, you'd have a ratio of 1 over 1. What's 1 divided by 1? 1, all right? So that would be 1 radian, all right? In terms of the picture, all right, if you have to figure that, let's just say the radius is that long from here to here, all right? If you could take that and measure out from here along the edge of the circle, all right, that would be 1 radian, all right, from here to here, all right? And there would be about 6 and change of these, you know, another one, 2 radians, another one, 3 radians. And because it's imprecise, all right, well, I should say it's extremely precise because it's pi, right, which goes to infinity, you end up with 2 pi of these, 6.28, whatever it is as a decimal, all right, would be the maximum. That would be the max in the decimal form. 2 pi would be the max in Pi Radian form, okay? This is favored when you're doing calculations often, All right. Gradients is interesting, but we don't use it too much in the United States, at least not in my life. This is the logic of, rather than breaking this up into 90 as from a perspective of a right angle here is 90 degrees, why not make it 100 exactly? Right? Why? Because 100 is a nice warm fuzzy number. That means that from here to here would be 100, and from here to here would be 200, and from here to here would be 300, and the whole way around would be 400. To distinguish it from ordinary degrees, instead of using a little naught symbol, they use a little lowercase g up in superscript. Anyhow, you're not really responsible for that. We're just going to be converting primarily between these two. All right? So let's do this now. All right? I'm going to turn the projector off finally, because it's cooking me. All right? Maybe put a little light on. I think I need to adjust my camera. I think that's better. It always drifts in the middle of the projection here. Let's do some examples finally. Oh, tenacious blue. I'll take this down because I would like some more light. Alright, and do some conversions. Alright. A couple of things. Right? For conversion, I want to teach you something that I was taught a long time ago in a chemistry class that is very practical for our purposes now. All right? We're going to be converting from degrees to pi radians and vice versa, and if necessary, to just full-blown radians. All right? In that event, there are some conversion factors that you should commit to memory, all right? And I'm going to give you to like this, all right? Depending upon what you're starting with and what you want to end with, all right? Know this conversion factor. This is known as a conversion factor, all right? Oriented with the pi symbol on top and 180 degrees on bottom. This is essentially the concept of one-to-one. It's written in two different systems. All right? So when you multiply by something that really represents the amount of one, it's from a logical standpoint, it's not changing the value of something. It's just changing the appearance of something. All right? This is basically used when you're trying to convert from degrees to pi radians, and you leave the symbol pi. You end up dividing by 180 is the bottom line. If, on the other hand, you were going the other direction, it's just the same conversion factor upside down. So you have pi on the bottom and 180 degrees on top. This is still a conversion factor. It's just for a different usage. All right. Essentially, this is when you were starting with pi radians and you're converting to degrees. Right. There are, in theory, two more of these, and I'm going to put them here or wherever I can get them to fit. I don't want to erase them. But it's the situation when you're trying to convert from pi radians to, say, just regular radians. So I'll put them in green. All right. And I'll put this shows up. Is that visible? Looks like it's okay, right? Pi over the decimal equivalent 3.14, I'm going to put little ellipses here because that's not really that visible. You suck, green. All right, I keep trying to like you, but you just suck. All right. Pi 3.14 ... because you want high precision if you can help it. Or you could have it as 3.14 ... on top and pi underneath it. It depends on what you're starting with and what you want to end up with. Now, there is this handout. I'm not going to turn on my projector. I'm just going to point at it for a moment. This is what I was taught in chemistry many years ago. All right. Think of this as being a conversion, a unit changing device. All right. Whatever you're given, right on the far left, write multiplication x, then put your fraction style conversion factor in the middle. And if you arrange it strategically, oriented either one thing on top versus one thing on the bottom or vice versa, all right, there'll be a cancellation effect, all right, via cross cancellation. And if it's just one step, it'll spit out what you want, all right? So given times the appropriate conversion factor rigged appropriately will give you what you want. And you decide this purely based upon the units that you have and the units that you want. All right, now there is times when you may have to do several conversions in the same problem, but once you get comfortable with the basic idea, and you could just duplicate this model if you like it, all right, you do it at will, you get really good at it, right? So don't panic, all right? So let's do a couple of examples. Green, let's look. That's actually right, all right? It's just not visible. All right. Let me give you these 3 examples. I'm going to try to confine myself, just not to have to stop to erase something. I have a tiny little board here. All right. Let's say we're going to convert as example 1 here. Example 2 here and example 3 here. 15 degrees into so many pi radians. I'm going to abbreviate radians as rad, which is radical meaning. All right, and then in this instance, we're going to convert what you would be understood as being pi radians into degrees, so backwards. Pi rad, if you'd like to put the word rad, that's cool. All right. A lot of times it's just not written. Let's say that you had, in the third instance, 3 radians, and you wanted to convert that into pi radians instead. Choose the degree that you are given. All right. If you have a number here, then you're given degrees. So I'm going to use green now and not care that it doesn't show up, because I'm just going to write my little model here. Given times conversion factor in the style of a fraction equals what I want. And I'll do it here as well. Given times the appropriate conversion factor is going to equal what I want. And then given times the appropriate conversion factor. What on earth is that? Oh. What I want. Sorry. That's my eldest sister. If you are given 15, all right, and it's in degrees, that would be here in the model. I have to get rid of the glare here, so sorry for that. So what you would do is you would take that, and I'm just going to superimpose it on that position, all right? There's a question mark here, if this is pi radians is what I want, all right, I'm going to put pi rad, all right? I better just check this, forgive me. Okay, so if you want to create a cancellation effect, basically the unit, and I know this is a funny unit, but it's the degree unit, has to be one on top and one on bottom. So of the 2 basic choices, what you see in red and blue here, the one that would create a cancellation effect in this case would be the one that you see sitting here, all right? So you have 180 degrees and pi on top. All right. Now everything else is good to go. Maybe this is overkill, all right, but if you have a little degree symbol here and a little degree symbol down here, this justifies cancellation because it's like something divided by itself, essentially. All right, that means, like, you could straighten up the numbers too if you want. What would be left over is 15 times pi on top. That would be here. And 1 times 180 would be down here. This is a fraction that you could whittle down, all right? And then you have your answer in pi radians. You want to ideally simplify it. So in the case of 15 and 180, they're definitely 180 is actually divisible by 15. All right, that's the GCF. All right, you could use your calculator. If you enter these figures into your calculator, it will automatically reduce them for you, but just to get through it without messing around with that, 15 divided by itself would be 1. 15 goes into 18 one time with 3 left over, which would be 30 is the difference, and that would just be 2. So this is pi over 12 radians in this case. If for whatever reason you wanted to convert this to a full-blown decimal radian, right, what you would do at this point, and I didn't ask that initially, is incorporate one of these conversion factors, right? One that would cancel the pi symbol, essentially. So here, I'll do that really quickly. If I were to then use pi over with 3.14 on top, the effect, again, a cross cancellation effect, would be this and this, right? The result would be 3.14159, whatever degree you like of it, divided by 12, all right? Let me show you something because it really must. On your calculator, there's an actual pi number, right? It's in blue here. So if you wanted to do, say, the extra portion of this to convert to the decimal, it would be second times the upward caret symbol. It's understood as this is 3.14159, whatever degree of precision that it is. All right, and then you'd hit divide by 12, and it will give you the decimal equivalent. So 0.2617, such and such. All right. At that point, this is the decimal version of radians, which is just called radians. 0.26, I'm just rounding, 18 radians, if they ask you to go that far. Okay, normally it's right here that where you would stop. Pi over 12 radians is the equivalent of what 15 degrees would be, right? Now, because you have this handout, I just want to show you that this does make sense, right? All right, here's that thing I mentioned earlier. They're not given to you, but here's the reference, all right? 30 degrees, which would be twice as much as 15, naturally, is pi over 6. All right, so half of this would be 1/12, all right? So the 15 mark would be somewhere in between 30 and 0, all right? Okay. All right, now let's say you start with pi radians and you want to convert to degrees. Again, analyze what you're given, all right? Put it here in the model. I'm just going to put pi over 6. And then, again, choose the appropriate conversion factor. In this case, what would cause a cancellation effect would be the blue version of this. So it would be 180 above the line over pi. All right. So pi and pi would cancel, all right? And then essentially it would be 180 degrees divided by 6, which is 30 degrees. All right. Pi over 6, as I just kind of flashed it from the diagram, all right, is in fact 30 degrees. They represent the same location, but in two different systems of measurement. All right. Let's say that you wanted to convert 3 radians into pi radians instead. All right. Again, analyze what you have given, put it in the given position. I'm going to put 3 rad. And then it's really going to be one of these two versions of it. It's pi, but then the decimal equivalent either written on the top of it or beneath it. All right. So if you want it to be pi radians as the result, all right, then pi has to be on top, and the decimal 3.14, whatever it is, would have to be underneath it. Don't use just 2 decimal places. I mean, it's not wrong really, but you want a high degree of precision. So in that event, I would use your calculator. All right. And what you end up with as a result of this is there's not going to be any simplification. You're going to get 3 on top and 3.14, whatever it is underneath it. And you'll have, once you do the division, something else. Let's see. Sucky thing though. The way it's going to end up, just unfortunately, is like you get a fraction that's not a nice fraction. So you got something like that. All right, 0.954, whatever it is. But it is in the style of Pi Radians. All right, 0.9. 5. Yeah, I'll just put 0.95 Pi Radians. This is rounded because it stretches, all right, well beyond that. If it's 95, 0.95 is 95 over 100. You could, if you wanted to, make that into the more or less normal way of looking at Pi Radians, which is the fraction style of it. All right. 95 over 100, and again, I really should be using squiggle equals because this is an approximate. All right. Divide these by 5. 15 would work. No. Yeah, I think you kind of get stuck with dividing by 5s. 5 goes in this once with 4, 19, and that would be 20. So this would be something like 19 pi over 20 radians. It's kind of crummy because it doesn't work out. It doesn't, because of the decimal, it's not going to be a nice thing. I rounded, right? So I'm kind of cheating a little bit, but that's what you would end up with, something like that. Almost a whole pi, right? 19 over 20 is just shy of 20 over 20, right? So not quite a whole pi. 3 radians is remarkably close to 3.14, right? That makes sense. All right. 19 times pi divided by 20. Yeah, all right. Look how close it is, all right? 2.98, right? I rounded too much. All right, but anyhow, that is the process nonetheless. All right, so basically, know that you have these tools, all right, conversion factors, and that you can at will shift the position of them if you need to cancel stuff. You ultimately decide what you want to cancel by based upon what you're given versus what you want, right? These are just things that involve basically one step each, but you'll see forthcoming examples where it may be multiple steps. All right. Now, I'm going to go back to what I was mentioning before, which is the coterminal angle situation. So if you look at this sheet, I'm going to go through these examples for coterminal, how to find them. All right. The basic gist of it is you want to take whatever is given to you and translate it into a more normal sort of number, right? In the usual spectrum, the usual range, for lack of a better phrase. right? When you're looking for coterminal angles, basically it's something in the, for lack of a better phrase, normal range of 0 to 360 versus whatever you've gotten. So you want something, regardless of what you're given, whether you give a negative or you're given something bigger than 360, you want something in that instead. It refers to the same location, that's why they're coterminal angles. Same location, smaller numbers. Or more normal range. Right? Okay, so here's two examples. I don't know why the board is getting so dirty today, because I did clean that. Here's two drawings. Suppose that you had something that was a negative angle given. Right, so you had something that was read that way, right? And it's negative 45 degrees, right? If you wanted to find something that was read instead of being negative, in the north, this is 0, this is 90, this is 180, this is 270, and that's 360 is coterminal with 0. If you want something that was instead read from this direction, counterclockwise is positive, same place, just it's going to be a different number. All right, then in that event, all right, you're going to add 360, all right, until in the usual normal range, all right, in the range of 0 to 360. So if you have 45, negative 45, negative 45 degrees plus 360, that'll get you in that spectrum, if you will, right? So what do you end up with? 315, right? This is equal to 315 degrees, right? So it may be negative 45 from the x-axis in the clockwise orientation, but from the better etiquette, shall we say, counterclockwise perspective, the coterminal angle is 315 degrees. It's positive, right? Right. If in theory you wanted a reference angle, the reference angle would be just the positive incarnation of this. Now, let's say that you had something that was many turns around. If you had something that was an angle much greater than 360, right, versus an angle that's a negative angle. Here's 0, here's 90, here's 180 again, here's 270, this is 360, right? If you went from 0, counterclockwise is the normal situation, one turn, that's 360, right? If you went another complete turn around, that would be 720, right? Right, 360 times 2. If you wanted to land in quadrant 1, say, that far extra, and you got to a point of 800 degrees, there's another 90 from 720 would be what? 810, right? Or 800, is it? What is it? Plus 90, 11, yeah, 810. That would be 810 here, so 800 would be somewhere in between, right? This is an example of an angle 800 degrees being greater than 360. All right, but we'd like something that's in the normal spectrum. So what would be the equivalent is the question. What's the equivalent that's just going that far, right? Not multiple turns, all right? In that event, what you're going to do is you're going to subtract 360, all right? Or in theory, if you're given radians, use pi, 2 pi, all right? Until in the usual or normal range. So this one will take maybe subtracting more than one time. So let's say hypothetically you had 800 and you subtracted 360. The question is, would you end up in that spectrum, like under 360 somehow? No, it's going to be, you know, close, but no cigar. So that's 10, that's 7, you get to 440 it looks like. Alright, so if this is just 440, right, do it again, right? So minus 360, and in that event, it would be 80, right? 80 degrees, right? So what's coterminal with 800 is something very similar looking, 80, right? They're in the same location, right? It's just using a smaller figure to explain that, right? It's in the, shall we say, normal range, okay? All right, let's do one that involves pi. Pi radians. Oh man. I may have to hit this with some alcohol because it's so really dirty. Let's say that we had to find an angle, we'll call it beta just because that's an option instead of theta, coterminal with 19 pi over 4, so kind of a yucky number, right? In the usual range of 360, otherwise known as 2 pi, right? Right. If you look at the reference, you're not going to find, unfortunately, because it may be several turns. What I'm getting at is, this is still good to have on hand, right? The reference that you see here in terms of pi radians, but if you notice, there isn't anything that matches that. So there's a process to get from here to there. Right? What you might do is this, right? Number one, convert to degrees so that you have some inkling as to what quadrant you're in, right? So if you have 19 pi over 4, all right, something is in pi radians if you see the pi symbol, all right? And I'm going to convert it 2 degrees via this conversion factor that causes a cancellation effect of pi. And see what you get. Pi would cancel this. You could try to whittle it, what do you call it? Whittle it down to something a little bit more warm and fuzzy. 4 and 180 would simplify. 4 divided by itself is 1. 180 divided by 4 would be 1. Pardon me, 4 with 2 left over 45. And then you get 19 times 45, which is kind of a sucky number, but right, it's in degrees at that point. So what 19 times 45 would be is apparently 855. So 855 degrees is well beyond the normal spectrum. All right, so here's a picture. All right, I'm going to convert to degrees, and then I'm going to draw. All right. If this is a positive, and it would be, all right, 850 degrees, and this is 0, and this is 90, and this is 180, and this is 270. And starting from 0, all right, one way around would be 360, all right. A second way around would be 720, all right. And then if you went this far up to what would be 90, that's 810. So you would have to figure that 855, all right, is something in here, all right. It's between 810 and probably what another 90 would be, all right. So you're in quadrant 2, all right. This is 855 degrees, otherwise known as 19 pi over 4, all right. What we would like to do is, rather than use degrees of 855, that's just because it may be not to corrupt you, but a certain level of comfort with degrees, all right. Rather than that figure, rather than its equivalent in pi, 19 pi over 4, we want something that's in this spectrum instead, right? Smaller numbers to explain the same place, all right? So rather than multiple rotations here, we just want to go that far, right? So how will we do that? All right, well, analyze what we have, all right? Is 855 a negative number? No, all right? 855, all right, 855 degrees is significantly greater than 360. So in a situation like that, we're going to subtract by 360 until in the normal range. That's not to confuse that. All right, so what does that mean? It means you may have to do this several times, but at 855 minus 360, what do you end up with? 945 apparently, 495 rather, sorry, which is close but no cigar. So do it again, all right? Minus 360, at this point you're in the normal range, all right? So 135 degrees, all right, is in the range of 0 to 360, so that's fine. But would like you to put it back into the style of measurement that it was given, Pi Radians. So that's the last step, right? You convert to degrees just to see if you feel comfortable with degrees, right? Draw a picture to help illustrate, then decide whether you're adding 360 or subtracting 360 based upon this number. And then once you get to the answer, 135, all right, convert it back to Pi Radians. So, step 4, convert back to Pi Radians. All right. If you have 135 degrees, think of that as being given. Right. You're now going to multiply by the appropriate conversion factor that will cancel degrees, which means the version of this that you would like that involves pi and 180 would have 180 on the bottom because of the degree symbol, right? The effect, though it's minor, right, is these units would cancel. You could simplify them before you attempt to multiply them. That's a good strategy. But the bottom line is that you're going to end up with this. 135 pi over 180. And since this is a fraction, you would ideally reduce that, all right? If you want to, you could whittle it down by dividing by 5 because that's divisible, or you could pull a trick here with your calculator. It maybe is worthy of talking about, all right? If you go into Math button here, and then scroll over to Num, you get that cool feature, if the software is up to date, of N/D for numerator and denominator, and you can intuitively enter these figures, 135 and 180, all right? And in that event, 135 on top, and 180 on the bottom. Now, let's see, this is what happens when you do it backwards. You have it as it is. When you hit enter, it will reduce the fraction. So 3/4, right? Which is cool, right? But it's 3/4 pi radians, right? How come? It is apparently you're dividing by 45, all right? That's the GCF. 135 apparently divided by 45 is 3, all right? And 180 divided by 45 is 4. So this is 3 pi over 4, all right? Let's see if we use our reference now, if 135 degrees is that as the equivalent. All right, so if you look at this, and you go over here, in quadrant 2, yep, 135 degrees is indeed 3 pi over 4, a fraction of a whole pi. All right, so that's cool. All right. Now for the last bit of this, we're doing the physics portion of the show here. Let me turn on my projector again. All right, and that's back in here. All right, let's talk about arc length and area of a sector. All right, let's turn this on. I really do think I need to, unfortunately, clean my board a bit earlier than I would. So I'm going to do that now because it's getting really messy. And it's just smearing around rather than actually erasing. So a little alcohol goes a long way. And the blue is especially annoying today. Because it's lingering. Okay. So that will help. Just a little bit. Is that close enough? Zoom in just a little bit, a little too much. All right. As I mentioned, arc length is basically the edge of a circle, all right? The edge of a circle that would be formed, all right, it's between these rays, right, of the angle, all right? And it's subtended is the phrase that they use, of the angle, subtended by the angle, all right? So if you just superimpose this here, all right? Anyhow, there's a formula as you see here. S is equal to the radius times theta. In this case, is the symbol for the angle. All right. Okay. Now, one thing that's probably a bone of contention is whatever you're given in terms of the angle. All right. To do the actual calculation, you're probably going to have to convert it to decimal. So decimal radians. All right. Say, for example, you were given this. All right, I'll put the example right here. All right, to find the arc length, find S, given by R equals 10. That's the radius equals 10 units, whatever it is, doesn't really matter. All right. And subtended by the theta equal to 215 degrees. Right? And do this in radians. Right, hopefully that's visible. And if not, I will get another black. This is no problem now too. All right. So we're going to use this formula. Just beware that we may involve, if we feel comfortable, a conversion factor. Why? Because here we have degrees that's going in place of the angle. All right. This is just 10 units. It doesn't even matter, right? I could put 10 very easily in here, and there's not going to be an issue. All right. If I put 215 degrees in here, and they're demanding that we have it in radians, all right, then we're going to have to incorporate a conversion factor, all right? So in this case, we're going to have two conversion factors because it just says radians, it doesn't say pi radians per se, all right? What I would advise in that event is this. Start out with putting the appropriate features in, and then just attach at will, all right, conversion factors. All right. So we're going to need two ultimately. We'll have the one that cross cancels degrees. So if there's degrees above the line here, I'm going to have one below the line here, and that would be the 180 pi version of the conversion factor, pi on top, and then something that will cross cancel pi's. We'll have pi on the bottom here, and then I'm just going to put the first couple of digits, but I'm going to use my calculator at that point. All right. You could use 3.14, but again, you would like a high degree of precision. All right. So use your calculator when you're getting a closer to the exact answer if you do. All right. So if this is rigged appropriately, it looks okay. Again, if you like, you could make this look like fractions like so. Put in multiplication x. All right. This is going to be canceled the degrees this way, and it's going to cancel pi this way, which means that the denominator is going to be 1 times 1 times 180. It's going to be something divided by 180 in the end. This won't be a degree anymore. All right. On top, it's going to be 10 times 215. All right. Technically times 1 because of the cancellation effect, but times pi, that is 3.14 decimal equivalent. So you would basically write this in your calculator. All right. All of this stuff is left over above the line, and 180 is on the bottom. So as long as you're careful, if you've rigged the machine ahead of time, carefully, conscientiously, all right, then what you could do is enter this 10 times, I'll show you after I'm done typing it, forgive me, times pi divided by 180. All right, so it's ironic perhaps, but if you want a very highly accurate answer, right, again, hit second and then the caret symbol to get the pi symbol. It's understood that this is 3.14159, whatever it is. Anyhow, 10 times that times 215, all encapsulated together, divided by 180. All right, and then you have it. It's like 38 degrees almost. Well, pardon me, 38 radians. All right. About 38 radians. All right, I've rounded it. All right. Now here's the area of the sector underneath here. There's a similar situation where you may need multiple conversion factors to get through this, but here's the area of the sector formula. The area of the sector of a circle with radius r subtended by angle, a central angle is technicality. All right, theta is measured in radians. All right, A is equal to 1/2 theta times radius squared. Okay. So in this event, if we were going to find, let me erase this just to get out of the way. For this problem, find the area of the sector formed by a radius equal to 20. In this case, you get an actual unit of feet. And an angle of 30 degrees, all right, in radians. You're going to end up with feet as the answer, all right? So the end result is not going to be radians, but when you're doing this calculation, you're going to convert this to radians first, right? Because you need a decimal, all right? So let's write out what the features would be. First of all, just to make it a little bit easier to see. Here's area is equal to 1/2 times the angle times radius squared, all right? So we have a radius. It is measured in feet, apparently. So there would be a 20 here, and we really should follow the order of operations because we're just dealing with one side of an equation. So we're just dealing with the expression here to simplify. We should square first before we start multiplying stuff, all right? Feet is going to be squared ultimately as well because it's an area, all right? Now the angle that is 30 in here, all right, as I said, has to be converted to radians. So there's going to be, again, a couple of conversion factors. If I were going to stretch this out, what I would do is this. Put a 1/2 on the end, all right? Take your number 30, and technically it would be above a line. It doesn't have to be, but you could stick a 1 there just to make it obvious. And then we'll put a conversion factor here. And there's going to be a second one because we need the decimal radians. And then there is this, 20 feet squared. All right. Again, because this is an exponent, it's an amped up version of multiplication. We really should deal with that first, which means 400 is the number that's going to be there. All right. So 400 feet squared is the end here. Technically over 1. All right. Now, the conversion factors that have to be in between are things that cancel out degrees. So 180 again on the bottom and pi on top. And then something that cancels out pi would be pi with 3.14, the decimal equivalent on top, whatever degree of precision you want to write it there. You're going to use your calculator ultimately. So the logic is this cancels this, and this cancels this. Good. All right. You could do a little simplifying. If you want, you could just figure out what the top is going to look like. Type that, enter that into your calculator, figure out what the bottom is, divide by that. All right. But I like to do the little bit of inventory that I can before I go to my calculator. All right. So there are some things that are fairly easy, like for example, if you just straighten out this point after you've dealt with the square. All right, if you straighten out 1/2 and 30, this is just going to reduce to 15 here. That means a 1, a 1, 180, a 1, because the pi's canceled, and a 1. The only thing on the denominator would be 180 then, and it's no longer degrees because of the cancellation effect. All right, top would be 1 times 15 times 1 because of cancellation, times pi, right, times 400, right? So 15 times pi in the 3.14 presentation, right, times 400. You can even further still, if you want to, whittle down these factors of 180 and 400 at least by 10, but it's fine. All right, this is already in feet squared because of the 20 being squared. And now you have this to type. Right, so clear tippy top 15 times pi times 400 divided by 180. Okay. So you have that all on top. I didn't simplify the denominator, I technically could have. And you get this, something like 105. All right. So this is about equal to 105 feet squared as an area. Okay. I might get rid of this one. It's crummy. Only on time, not bad. Okay. Now, underneath this is the rest of the formulas as they would be presented in our textbook. these are really the most relevant. Angular speed, linear speed using arc length, and something that relates them directly. Linear speed as directly related to angular speed. All right. I made a diagram myself, which I want to show you because I wanted to explain this. So take a look at this for a moment. Here are speeds, all right? Let me back off a little bit. There we go. There's linear speed and then there's angular speed, all right? You can translate something that is moving circularly, all right, into linear speed, all right? It's sort of like if you can imagine lines painted on the street. All right. The roller that they use is a device, if you've ever seen somebody painting the white lines on the street. There's a roller which has paint on it, right? And it just picks it up and takes it off the ground, and picks it up and takes it off the ground and puts it back as it's moving forward, right? The little paint roller is rolling, all right? That's circular motion, all right? But it's still moving in the forward direction, all right? Anyhow, the formulas that we have could be, linear speed could be translated to or from circular motion, right? What's important maybe to think about it is, in the context of this formula, what is being used? Arc length, all right? Per meaning divided by time, all right? If you remember the old distance formula, all right, that distance is whatever speed you give in times an amount of time, you could rearrange it so that you're solving for speed instead of for distance. In that event, it would end up being this, distance divided by time, all right? What's happening in our case is that we're not sticking with the usual symbol for distance, which is x, all right, in a physics class, right? What we're opting for is s, arc length, all right, over time. All right, it's abbreviated as V, unless it's new, it might be a Greek letter. Is equal to S, the arc length, just understand the S doesn't stand for speed, it's arc length, it's capital S, over T, all right? There's a similar formula, because it has the same basic idea as two things divided, and one of them is a distance of sorts, all right? But it's the angular speed, all right? What's the difference between these? Well, as concisely put as I think, arc lengths are per unit time, all right? Pardon me, linear speed is arc lengths per unit time, whereas angular speed is angled rotations per unit time. This is using, rather than the edge of a circle, all right, as a length, all right, this is using a number of degrees perhaps, or probably more likely, radians, all right, per unit time. All right? It's in a bigger picture, all right, linear speed is translated again to or from circular motion, all right? It can be translated maybe from this perspective, it would be easy to think about it. It's taking circular motion and expressing it linearly, all right, just maybe because we're more comfortable that way. Angular speed is really defined by circular motion because it involves an angle, all right? Anyhow, you could see the similarity at this point, all right? Instead of, if this isn't a V, I think it might be the Greek letter nu. It is a distance divided by a time, all right? Over here, this is omega. It's a lowercase, it looks like a W, right? But it's actually lowercase omega, right? Another Greek letter, all right? And it incorporates an angle instead of an arc length, all right? Still divided by time, all right? Now, what else is mentioned in the book is what you see here, all right? But how do you get to this, all right? In a nutshell, all right, it's from these, all right, and also the arc length formula, which is S is equal to R times theta, all right? You can derive that, right? And that's a beautiful thing because it actually converts angular speed directly into linear speed. So it's kind of cool for that reason, right? How so? Well, if you have this as your angular speed formula, and this is the arc length formula, and you rearrange this to solve for theta, and then insert what would be the rearranged version of this would be omega times time in place of theta, then you get this, right? So the arc length can be determined by the radius, the angular speed, and time in theory, right? If you then take that and incorporate that into the linear speed formula, right? In place of S, you would have RW, not RW, but R omega T, all right, over T, which means there's the cancellation effect, and the times would cancel. That leaves you with just radius to use and angular speed. Right? Again, the beauty of this, and the reason why it's cool, is that it converts directly from one type of speed, namely angular, into linear, or vice versa if you need to rearrange it. So that's tops to me. All right. All right, let's do a couple of examples. There is these word problems here, and then I'll stop. This is getting really hot. All right, I swiped this from your book. And I'll take this down because I don't think it's necessary anymore. Let me see if that's visible. Looks like it's okay. All right, it's hard to read from far away. Let me read it. All right, a water wheel, shown in figure 24, completes one rotation every 5 seconds, right? Find the angular speed in radians per second. All right. So we have a formula already. Angular speed is theta, an angle, and this has to be in radians per second. This has to be, it's specifying that it wants seconds. So I'm going to abbreviate seconds as SEC, all right? They don't give us a lot to go on, but we can infer a lot, all right? This statement here, one rotation every 5 seconds, all right? So we are ultimately going to divide by 5. Sorry, put this over here. But we do have to do ourselves a little bit of a favor, all right? Translate the word rotation, right? One rotation implies a lot. Implies, right, if you feel more comfortable, a certain number of degrees around something, right? Just one rotation, right? If here you have a circle imposed upon a coordinate axis, here's 0, here's 90, here's 180, here's 270, and here's 360 again. One complete rotation would be from here to there, right? So if you're familiar with degrees at least, one rotation implies 360 degrees, all right? But we're going to need to have this in radians ultimately, so what we're going to do is we're going to convert 360 to perhaps pi radians first, and then to just regular radians, and then basically divide by 5, all right? So if you have 360 times 180, the 180 on the bottom specifically will cross cancel the degree unit, and you'll have pi up here, and then you have a second conversion factor which will get rid of the pi symbol because you'll be using the actual decimal equivalent. Okay, so if you rig that, right, this cancels this, and this cancels this, 1 and 1. And then what you end up with is essentially 360 times the equivalent of pi. 3.14, whatever it is, over 180. Right? And the result will be you have actual full-blown radians at the end. Right? So on the tippy top of this, 360 times 3.14, whatever it is, times well, that's it. Radians. Underneath it, you'll have 180, right? You could, because it's in factored form, the way that I've written here, right? And then underneath all of this is 5 seconds, right? Ultimately, you're going to straighten this out first, right? In theory, it's a complex fraction, so this is dividing by 5. You could put 5 on the bottom, all right? If you want to prep it that way to begin with, all Dividing by 5 means that you're going to multiply by its reciprocal, which means that you would have, in theory, 360 times 3.14, whatever gobbledygook it is, over 180 times 5. Right. This, if you prepped it completely like so, is what you would enter into your calculator. So, is this really that bad, this marker? Jeez. All right. So, yeah, you gotta be very careful. 360 times pi, close parentheses, hit division symbol, and then since I have two factors in the bottom, I'm going to encapsulate those as 2 as well, 180 times 5. And you might enter it like this. All right, 360 times pi, this is going to be the decimal, divided by whatever 180 times 5 is. All right, and there we have it, 1.26 radians per second, if you round it. All right. All right. Because that's the unit on the bottom. This is about 1.26 radians per 1 second. Something like that. Okay. Now I'll free up some space. I'll do one more. Down here you see a bicycle has wheels 28 inches in diameter. A tachometer determines the wheels are rotating at 180 revolutions per minute. Find the speed of the bicycle is traveling down the road. Now they don't specify that they want it in miles per hour, but I'll do that as an afterthought. What you should end up with, because they mention inches, is inches in an amount of minutes. Inches per minute, which is kind of an awkward way of talking, perhaps. But it's doable, right? So, I'm sorry this is so distant, so it's kind of hard to read from far away. Let me just kind of emphasize certain points. Do I have another black? No, of course not. We start with this. We have a diameter, right? Because we're talking about a bicycle wheel, right? A diameter is the distance across the center. It's a funky, looks like a Pokeball now. The diameter is equal to 28 inches, right? That means that in theory, halfway, the radius would be 14 inches. All right. If we're trying to find the speed of the bicycle that's traveling down the road, this is without saying the word linear speed. Linear speed means that we're going to use probably, if not this version of the formula, s divided by t, right? Then perhaps we will use this version of the formula, r times omega, right? Which one of these would be more appropriate in this case? You probably can do it either way, but there might be more work if you do it this way. Why? Because they actually did tell you wheels rotating at 180 rotation revolutions per minute. That's an omega. It's just not a nice one, for lack of a better phrase, right? And we have something that we could glean from that, right? That figure. So I'm going to go with this because we already have a radius from cutting a diameter in half. So 14 inches is something that would fit in here, but we need to conclude what the angular speed would be first, all right? And we kind of have it, it's just more or less disguised here. So if it's 180 revolutions per would be this line, minute, all right? This is what we have for an angular speed to begin with, all right? I wonder if we could get away with just using that. We might, but it's not, no, I think we're going to have to convert it to a decimal, so, yeah. We're going to have to contrive a conversion factor, right? Because this isn't even in pi radians, right? We have an angular speed that is not in degrees, right? It is also not in pi radians. It's not even in regular radians. We have this sort of record player style of speed, all right? But so we can nonetheless figure it out. And here's how you would do that. We're going to say, all right, well, that's a rate, all right? This per here. So I'm gonna invent, right, because I have to, a conversion factor for this to start with. All right. What can I do to get rid of revolutions and maybe replace it with one of these three? Well, what seems maybe the easiest thing to do is, since I'm going to have to go to radians eventually anyway, is start with pi radians. So if you think about a complete trip around a circle, in degrees it would be 0, 90, 180, 270, back to 0 would be 360. Right? That's one complete revolution, right? If it was using pi instead, it would be this. It would be 0 pi, pi over 2, right? Is it just pi for 180? 3 pi over 2, and then 2 pi, right? One way all the way around is 2 pi, right? So therefore, one revolution is 2 pi to start with, okay? Let's go with that, all right? Yep, okay. So, this is going to strategically cancel revolutions, all right? And ultimately, it's going to be 2 times 180, which is 360, with a pi attached to it, all right? So in here, for angular rotation, 2 times left over 2 times left over 180 is 360 pi, okay? That, if you multiplied it, 14 times 360 is 5,040 with a pi symbol attached to it, because it's still pi radians, right? I need a little bit of extra space, so I'm going to erase this. Okay. So, linear speed, assuming that's what they're asking, is 14 inches times 360 times pi, all right? And if in the long run, what I would like is a speed that's more or less in the normal vernacular, perhaps we will convert this to miles per hour at some point, all right? Bear in mind that this is just, right now, I'm going to put a little thought cloud here, 5,040 pi radians as a speed, all right? It's not wrong, but it's not in the unit that would be maybe more comfortable, all right? So, and there's inches attached to this as well, all right? Because I didn't cancel inches. So, I'm gonna just put inches in here as well. 5,040 pi inches, technically, times radians, right? So, oh, and you know what else? Let me just remind myself too. If this is 180 revs, it's per 1 minute, all right? So even after I do this, even after I take out the revolutions and leave it with pi, all right? Yes, revolutions is going to cancel, all right? Pi would be left over, but the unit that would be left over here would be a minute down at the bottom, okay? So taking it this far would be inches per minute, right? Okay, so to get from here inches per minute, all right, I'm going to convert 60 minutes into 1 hour, so that will be the denominator ultimately, and then introduce another conversion factor that converts inches to miles eventually. Now, I don't know a direct one, but I know an indirect way of doing that, which is this. Inches is above the line. 12 inches is equal to 1 foot. Right. That's getting me closer to miles, but still not quite right. So I'm going to have a third conversion factor in theory, which is 5,280 feet is 1 mile. Okay. Now the way that this is rigged, right, is minutes is on the bottom from revolutions per minute. It never gets canceled out. All right, maybe I should turn this off because unfortunately it's kind of conflicting a little bit. Make it easier to see. All right. Inches is left over from getting rid of revolutions. So that's down there, and I just didn't do the multiplication at this point. That's what it would be if I did the multiplication. All right. Minutes is going to ultimately be canceled by this conversion factor above the line, below the line. And that will leave me with hours at the end. So many hours, right? And so many miles, right, at the very end. Hours is left over. This is a 1. That's a 1. Inches is going to cancel here and here, all right? And feet, which is in the middle here, is going away as well, right? That's how miles gets left over. There is one thing that's still missing though, all right? It's the conversion factor for pi, all right? In theory, all right, if I put in 3.14 over pi, the pi's would cancel. So what I might do, just as a shortcut, I hope you forgive me, is just put myself a little reminder here that this is 3.14. All right. So I have 14 times 360 times 3.14. All right. So 5,040 times 3.14, same difference, same product technically. Times 60 times 1 times 1. All right. That's all the stuff that would be multiplied on top here to get to this point. This is what would be on the bottom to get to this point. I have to throw this marker out. It's actually frustrating me at this point. Adios. All right. So let me get the gobbledygook out of the way, and we'll type what we need to. All right. We're gonna type 14 times 360 times the equivalent of pi times, should be 60 technically, alright, times 1 times 1, so that's not necessary. Alright, that would be the stuff that would be immediately left over. Alright, on the bottom there would be 12 times 5,280, because that's how many feet there are in a mile. I happen to know that. They used to make us memorize that stuff years ago. Anyhow, if you want to, again, because this is entirely factored, you could nonetheless refine this before you enter it. All right, but it's cool. It should work. All right, let me do it, and I'll tell you. All right, 14 times 360 times pi. I'm using the pi symbol on my calculator. Times 60. Divided by the denominator of 12 times 5,280. Right. This should be okay. Right. It's not the most elegant way to do it, but it would work. Alright, that's the whole thing as I've typed it. Let's see what we get. Yep, almost 15. Alright. This ends up being, when all is said and done, about 15 miles per 1 hour, right? Or on street signs, you'd see it MPH, right? Miles per is the line, 1 hour, MPH. It's about that, because it's 14.99, whatever it is. Okay. Alright, that's it. A lot of stuff, right? Alright, thank you guys for sticking with me. Anticipate you probably have homework from section 7.1, but I gotta look at it and edit it, okay? This video is for Tuesday. I'll see you again on Wednesday. Alright, be careful out there.